In our study of the circle, we have discussed the main properties of a circle involving radii and diameters, and how these two specific lines are involved in the creation of arcs. We learned in the last lesson that central angles have a special relationship with the measure of an arc. In this lesson, we will learn about arcs formed by chords and the inscribed angle formed by two chords. Firstly, let's begin with a review of what a chord is. In the lesson about the properties of a circle, we discussed that a chord was any line segment with two unique endpoints on a circle. I mentioned that there were an infinite number of chords that could be formed. Let's look at these two chords from circle Q. We don't know if the two chords are congruent, but let's say we measured their distance from the center and found they were both 1 centimeter away from the center. With this information, we can conclude that the two chords are in fact congruent since the information satisfies our next theorem. In the same or congruent circles, two chords are congruent if and only if they are equidistant from the center. Since chord RU and ST are the same distance from the center, we can safely conclude that the two chords are congruent. Now that we know these chords are congruent, our second theorem gives us insight into what we can conclude about their respective arcs. In either congruent or the same circles, two minor arcs are congruent if and only if their respective chords are congruent. Looking at circles Q and W, chords RU, ST, and ZY are all congruent, measuring 3 centimeters. According to this theorem, we can logically conclude that arcs RU, ST, and ZY are all congruent, since their respective chords are congruent. Our third theorem involves the bisection of arcs and chords. If a radius or diameter of a circle is perpendicular to a chord, then it bisects the chord and the chord's arc. The converse is also true. The perpendicular bisector of a chord is a radius or a diameter of a circle. Examine circle E. Since radius EH is perpendicular to chord FG, you can conclude that line segment FJ and JG are congruent with one another, and that arcs FH and HG are also congruent. Looking at circle L, with the converse of our theorem in mind, we can correctly assume that line segment RQ is a diameter of circle L and is a perpendicular bisector of chord MN. Our next area of study involves the inscribed angle, which is an angle with its vertex on the circle and two sides containing chords of that circle. Looking at circle A, angle DBC is an example of an inscribed angle for this circle. These angles differ from the central angles we discussed in our previous lesson, since the vertex of inscribed angles are located on the circle instead of the center of the circle. This change in location also changes the relationship between the angle and its arc. These new arcs are called intercepted arcs, arcs with endpoints on the sides of an inscribed angle, which span the interior of the angle and each endpoint. Arc DC is an example of such an arc. The calculation of the measure of this arc is not simply the measure of the inscribed angle, like the arcs corresponding to central angles. The inscribed angles theorem states that if an angle is inscribed in a circle, then the measure of the angle equals 1/2 the measure of its intercepted arc. We can use two formulas. Theta equals 1/2 times the measure of its arc, and the measure of an arc equals 2 times the measure of its inscribed angle, where theta represents the inscribed angle measure. These formulas help us calculate the values of either the arc or the inscribed angle that intercepts the arc, depending on the information that we know. Since we know that angle DBC was 52 degrees, we could plug in 52 as our inscribed angle measure, theta, and multiply this value by 2 to calculate the measure of an angle's intercepted arc. 52 times 2 is 104, and the measure of our intercepted arc, DC, is equal to 104 degrees. Interestingly, this theorem logically leads to our next and final theorem. Because the same arc can be intercepted by many different inscribed angles, any angle that intercepts the arc should be congruent by virtue of our previously stated theorem. The same arc being intercepted by different angles never changes in terms of measure or length, and therefore, since the angle measure of the inscribed angle of an intercepted arc is always half the measure of the arc itself, the measures of all inscribed angles that can intercept this arc must be congruent. Here's the theorem. The multi-intercepted arc theorem states that if two or more inscribed angles of a circle intercept the same arc or congruent arcs, then the inscribed angles are congruent. Circle A has two inscribed angles intercepting arc DC. Since they intercept the same arc, we can conclude that the inscribed angle DEC measures 52 degrees, since the theorem states that both angles are congruent. In the next lesson, we will examine theorems related to secants and tangents, which are lines that interact with the circle from the outside.